For decades, the power of semiconductor fab was measured in hardware. The biggest lithography tools, the cleanest rooms, the most advanced machines money could buy. But today, something else decides who wins. It's not just the tools, it's the code running them. Software now predicts failures before they happen, adjusts processes in a real time, and determines whether a wafer becomes a profitable chip or scrap. The future of chip manufacturing is no longer only built in steel and silicon, it's rewritten in software. Hello and welcome back to Chips Weekly by Diana. I'm Diana and today we are exploring one of the quietest and yet most powerful shifts in the semiconductor industry. As chip making approaches physical limits, hardware alone is no longer enough. The competitive edge has now moved up the stack into data, algorithm, and software control. This episode is about how semiconductor fabs are becoming software-defined systems, and why the fabs that master code will dominate the next decade of chips making. Modern chip manufacturing is one of the most complex industrial processes humanity has ever built. At advanced nodes, a single chip can require over 1,000 tightly coupled process steps. Each step depends on parameters so precise that deviations are measured in angstroms. At this scale, humanity intuition breaks down. Even the most advanced hardware, EUV scanners from ASML, etchers from Lam Research, deposition systems from Applied Materials, cannot deliver results on their own. They need constant, intelligent control. That's where software becomes essential and not just optional. Modern fabs no longer operate on fixed recipes. Instead, they function as adaptive systems that respond to data in real time. Thousands of sensors continuously monitor tool behavior, process drift, and contamination levels, and, of course, pattern fidelity. This data feeds into the software platforms that adjust parameters on the fly, sometimes also wafer by wafer. As companies like TSMC, Intel, and Samsung, AI-driven systems now detect abnormalities hours or even days before a human engineer would notice them. The result is fewer surprises, higher uptime, and dramatically improved yield. One of the most powerful tools inside the software-defined fab is the digital twin. A digital twin is a software model that mirrors a real tool, process step, or even the entire fab. Engineers can simulate changes virtually, adjusting materials, geometries, or timings before risking a single wafer. Companies like Applied Materials, ASML, and Siemens use these models to explore thousands of process variations in software. What used to take months of physical experimentation can now be tested in days, with far less risk and cost. At advanced nodes, yield losses rarely come from obvious failures. They come from subtle interactions between steps that may be separated by hours or days in the process flow. Software platforms now correlate signal across the entire fab, connecting inspection data, metrology, and tools logs into a single analytical view. This is why the companies like KLA dominate inspection and yield analytics, and why Synopsys and Cadence are exported beyond design into the manufacturing software. Yield improvement today is driven less by new machines and more by better data interpretation. A modern fab runs on a layered software architecture. At the lowest level, real-time control systems interface directly with tools. Above that, process control software dynamically tunes parameters. Higher up, AI model predicts failures, optimize yield and flag risks. At the top, factory orchestration software manages scheduling, energy use, and throughput. In many ways, a fab now resembles a data center. Except the workload is physics, the factory itself has become a compute system. This shift changed everything about how fabs compete. Two companies can buy the same machines and still achieve wildly different results. The difference lies in software, in how well data is collected, interpreted, and acted upon. That's why TSMC invests heavily in proprietary manufacturing software. Why Intel is rebuilding its fabs strategically around software-first control. And why Samsung is embedding AI deeper into process optimization. Hardware can be purchased, software intelligence compounds. Here's a deep implication. A software-defined fab improves with time. It learns, it adapts, and its advantages become harder to replicate. As a result, semiconductor leadership is no longer determined by capital expenditure alone. It's determined by who controls the algorithms that run the factory. The future's chipmaking won't be won by machines alone. It will be won by the code. So the next time you hear about the new fab or a new node, remember this. The most important innovation may not be the tool, but the software controlling it. Chips are still made of silicon, but the fabs are becoming digital organisms. And in the years ahead, the smartest factors, not just the biggest ones, will shape the future of technology. What do you think will matter more in the long run? Better machines or better software? Let me know in the comments. And if you enjoyed this episode, like, subscribe and share it. And as always, stay curious, stay sharp, and stay chip aware.